Hi, the gradient descent is applied after getting the error from the given model. Suppose you assume the data set is given. From the data set we have calculated the predicted output y dash, that is sigmoid of g given 1 over 1 plus e power minus g. So here we will get the predicted output. Actual output y is given in the data set. Then we can calculate the error by using the cost function. Cost function j is here with respect to parameter theta equal to the binary cross entropy, that is minus summation of I equal to 1 to m y of ith sample and multiply with log y dash of ith sample minus 1 minus y of ith sample into log of 1 minus y dash of ith sample. So from this cost function we will get the error for all the samples m. Now how to reduce the error if there is a misclassification available? So for that we will go for gradient descent with the number of iterations. The objective is here to minimize the error between the actual output and predicted output by changing the parameter values theta. The gradient is the extension of a derivative in multidimensional space, which is providing you the direction along which the loss or error is optimally minimized. For example, our output, we have calculated the output by using the function sigmoid. So that output is, you assume, which is available here. This is the cost, okay, error, right? So but error is very high. For example, you look at that, this is around, it is 2. Okay, error, the difference between the predicted output and actual output is 2. So we have to reduce this into the value close to the 0 here. We have to bring this into 0. So how do we do this? By applying the gradient function, we can do it by applying the iterations, number of iterations, by updating parameter value for each iteration. So this is the new theta value is calculated for each and every feature. Here our g is having theta 0 plus theta 1 x1. So just we will have single feature. So we have to update the theta value for theta 0 and theta 1. So new theta j equal to old theta j minus learning rate alpha into dou by dou j theta j with respect to error we have calculated here. So when you are applying the number of iteration, you look at that: first iteration, second iteration, third iteration, fourth iteration, fifth iteration, sixth iteration, seventh iteration. At eighth iteration, you got around 0 value, close to the 0 value. So this is optimal one. So here this is called optimal parameter values. Okay, so then we can stop the execution. So when you are giving this theta value, our model will give very high accuracy. So that's what given here. We have to repeat that until we are getting the optimal parameter. That's what given here. So how many iterations? Around, I think, 8 iterations are given. So 8 times we have to repeat the same thing by updating the new theta value from the old theta value by using the gradient descent function. So here after calculating the gradient descent, you can get the optimal model from the logistic regression. By summarizing the all previous videos, first we have to do the pre-processing of the data for applying the logistic regression. Then we can give the logistic regression to the training data set. So here we have to mention solver, which logistic regression solver we can use. There is multiple solvers are there here: Newton -cg, lbfgs, lib linear, sag, saga. By default the logistic regression solver will be lbfgs. So this is the scientist name, limited memory bfgs. So F for Fletcher and BGS are other scientist name. Here again, yeah, if you use the multi-class, you can give the OVR, that means one versus rest. This is for binary class. When you are giving the OVR, it represents the binary class classification. So this will give you the two classes for all the data points available in the given data set as a class A and class B. If you are applying the multinomial means, it will give you the multi-class classification. So for that, you can take different solvers, Newton CG, Saga, and LBFGS. So here LIB linear is limited to one versus rest schemes. So you cannot use it for another Newton CG's GA for one, LIB linear. Okay. So once you apply the logistic regression, you will get the model ready. That is the trained model. Once you apply that, then you will get the trained model. Then you can pass the new data set, new data samples, test data, that is called test data, to the trained model to predict or validate our model. So that will give you the performance with respect to accuracy and F1 score, precision, recall, etc. So finally you can visualize the test result in the form of this kind of plot. Thanks for watching.